All right, math nerds. Today we're going to start talking about certain applications for function composition. And we all know that in a math class, when you say applications, what you really mean is word problems. So, yep, that's exactly what we're going to be taking a look at today. So hopefully you all have the guided note sheet printed out or at least up on your computer so that you can actually watch and follow along. So I'm going to be going through and working through each one of these 3 problems with you guys. Hopefully it all makes sense at the end. Once you start thinking about it, again, this is actually like pretty cool, useful stuff. So the first question we have says that a pebble is tossed into a still pond. It creates a circular ripple that increases in size over time. Every second, the radius of the ripple increases by 20 centimeters. Find the area of the ripple circle after 3, 5, and 8 seconds. So, generally, anytime I'm doing a problem like this, if there's a way that I can draw a picture to illustrate what's happening, I'm going to try and do that. So, that's what I'm going to do here. I'm going to attempt to draw a circle. At the center of that circle is where the pebble got dropped, and its radius, of course, is the distance from the center to the edge of the circle. Okay? So, for the radius, I know that there is a relationship. After 1 second, the radius is 20 centimeters. After 2 seconds, it's got to be 40 centimeters. Again, because it says every second, the radius of the ripple increases by 20 centimeters. So then after 3 seconds, it's got to be 60 centimeters, okay? And it would keep going and going and going. But the mathematical relationship that I'm establishing here is that the radius of the circle is dependent upon the amount of time that is passed. So we would say the radius of the circle, which is dependent on the amount of time that has passed, okay, it's going to be 20 centimeters for every second. So we can define the radius in function notation to be r of t equals 20 times t. English translation, the radius of the circle is dependent on how much time has passed since the pebble was thrown in. Every second, the radius increases by 20 centimeters. So 20 times 1 second is 20 centimeters. After 2 seconds, 20 times 2 is 40. After 3 seconds, 20 times 3 is 60, and you see where this is going. But we've now been able to go and use function notation to define the radius. But the question isn't asking me to find the radius, it's asking me to find the area, okay? So I'm trying to go through and find the area. Yeah, let me grab that highlighter. Now things are popping. So, how do I go through and figure out the area of a circle? Hopefully you remember this from your time in geometry, where you know that the area of a circle is equal to pi r squared. Okay? So, writing this in function notation, we can say that the area of a circle has to be dependent on something. What is that area dependent on? Well, pi is a constant, okay? 2 is an exponent, so it just depends on your radius. So the area is dependent on the radius, and we can express that as a of r equals pi r squared. So hopefully you're starting to see how we're going to end up going through and using a composition, because we've got a radius, which is defined by time, and an area, which is defined by radius. Okay? So let's go through and just think logically how we would come up with the answer. Okay, so let's find the area after 3 seconds. Okay? So if we were doing this and we weren't even thinking about function composition, if I wanted the area after 3 seconds, I know that ultimately I want an area. But to find an area, I have to have a radius. So first, I got to figure out what the radius is. Okay? So after 3 seconds, I'm really finding r of 3. Okay? So 20 times my input of 3 gives us 60. Okay? And that really should be 60 centimeters. Okay, so we know what the radius is. Now that we know what the radius is, we can plug that in to the area of a circle formula. So we've got A of, what's the radius? 60. So that will equal pi times 60 squared, because r is our input value, our radius, so we're inputting our value there. So 60 squared, probably a number you don't have committed to memory, so I'm going to go ahead and say let's use a calculator for that. So the area of that circle would be equal to 3,600 pi, I'm not going to make it multiply by pi, but it would be 3,600 pi centimeters squared, okay? Because area is always a squared unit, all right? So we could, in theory, go through and do that exact same process for 5 seconds and 8 seconds and come up with our answers. But we want to find a more efficient way to do that. The more efficient way that we're going to go and do that is by thinking about what did I just do, okay? And we want to turn it into a composition. So first, when I was solving this for 3 seconds, I had to go through and use the input of t to find the output of r. So I had to plug in time to find the radius. And then second, I could go in and use the radius to find area. So every single time I'm doing this, 3 seconds, 5 seconds, 8 seconds, anything else, I'm going to be following the same process. I'm always going to have to use t to find r, and then I'm always going to have to go through and use r to find area. So why don't we just skip the middleman here, okay? Why don't we go and take a look at how we can turn that into a composition, okay? In this problem, we first found r of 3, and then we made that the input to what? Okay, that became the input for A. So we really just went and found A of r of 3. So how can we describe that in the general case? Well, we would find A of r of t. So what would that function composition look like using r of t and A of r? Well, that would be equivalent to pi times r of t, which in this case is 20t, and then that's our input, and we're squaring it, because it's pi times input squared, so it's pi times our input, which is the radius function, squared. So working that out, we'd end up with the general case composition for this would end up being 400 t squared pi centimeters squared. Because again, this is all for area. So we came up with this general case composition of A of r of t, which is equivalent to 400 t squared pi centimeters squared. Okay, so let's go see if this actually works to answer all of those questions. Okay, so let's go through and we'll find the area at 3, then we'll find the area at 5, and then we'll find the area at 8 seconds. Okay, so we're going to go through and use our function composition. Hopefully for area of 3, we get the same thing that we did before. So we're going to say that the area at 3 is going to be 400 times 3 squared pi centimeters squared. So if we go and grab our calculator, you'll see that 3 squared is 9, and 400 times 9 is 3,600 pi centimeters squared. Is that exactly what we found before? It is. So that's got to work. Okay, the area at 5 seconds, we're evaluating the function a of r of 5. Okay, so a of r of 5 is going to be 400 times 5 squared pi square centimeters. So we go through and do a little bit of calculating, and we should get 10,000 pi centimeters squared, or square centimeters. And if we do it at 8 seconds, we're really evaluating A of R of 8. And we're going to say that that would be 400 times 8 squared pi square centimeters, which would give us 25,600 square centimeters. Okay? So while it may not seem like this is the easiest or fastest way to do it, please rest assured, this is not a difficult problem to calculate once. It may not even be a difficult problem to calculate 3 or 4 times. But say I wanted you to find the area of this particular ripple in the pond for 0 to 100 seconds. You can cut the amount of work that you do in literal half by just doing a function composition, okay, as opposed to always having to start from the very beginning on every single time. Okay, so what we've been able to do in this problem is we came up with a general case function composition, which was this right here, okay, and then we applied that to 3 seconds, 5 seconds, and 8 seconds to be able to determine the area of the circle that was being created at each one of those time intervals. All right, so let's go take a look at another one, okay? This one we're going to call the bargain hunting problem, okay, sales and discounts. If you guys have ever gone through and seen things at stores where they say, you know, take an extra 25% off, you know, save $10 off your purchase of $35 or more, and you've wondered, well, gee, how do they come up with what the final amount that you're supposed to pay is? Well, this is really how they're going through and doing it. Those cash registers have composition functions built into them. So we're going to take a look and see how each one of those works. So the problem we're going to look at right here says that you have a $50 off coupon, and you see in an advertisement there's also a 10% off sale at your favorite electronics store. You want to buy a new TV that is listed as costing $799. So first, we're going to go and express the cost of the TV for each of the price discounts separately. All right, so let's think. The first thing that I see up here is this little coupon. The second discount I see is the sale. Okay, so how is the coupon going to affect the price? Well, with the coupon, you're taking $50 off. Okay, with the sale, you're taking 10% off. So if you're taking $50 off, that would mean that you have the retail price of $799. We're assuming that that's including tax for the purposes of this example. You would take $50 away from that, and you would end up with $749. Okay? If you wanted to go through and take 10% off, you could do it one of two ways. The longer and more complicated way would be to say that you had $799 and you're going to subtract 10%, which expressed as a decimal is 0.10 times the cost. Okay, so that is the cost minus 10% of the cost. Okay, that would end up getting you $719.10. Okay, I'll go ahead and tell you the easier way to do that problem is to think to yourself, 10% off is 90% on. So $719.10 is just 90% of $799. That's fewer operations that we got to go through and do. But because we said 10% off and we're trying to show you guys how this is a composition, we'll go ahead and illustrate it that way. All right. So if I'm going to go and take these and then say, well, how can I express that using some sort of function notation? Well, I can say that for this one, it's a coupon. So if I use the coupon, okay, then the price with the coupon is going to be the original price of the item minus 50, okay? If I want to go and apply the sale, so we'll use S, then if we're using the sale price is going to be the full price minus 10% of the price, which simplified is just 0.9 of the price. So like I just said, 10% off is really like 90% on. Ergo, we can go and just simplify that operation that way, and that makes it a little bit easier for us to go and comprehend. All right, so now we can take a look at the next part of this, because we've already expressed the cost of the TV for each of the price discounts separately. So now we're going to go and say, let's decide if you should use the coupon first or second to the sales price, and what will the price difference be. Okay, so that means we're going to have to be doing a little bit of a comparison. All right, so first off, let's go through, and because coupon was first, let's do coupon, then sale. Okay, and over here, let's do sale, then coupon. All right, so if you go through and you were to buy this, and we're just thinking about the numbers, right? You would start off with an item that was $799. You would take away $50 from the coupon, which would get you $749. So essentially what we're doing here is we're applying the coupon price to this, okay? That gets us that $749. Then I would go and take 10% of that away, okay? So if we subtract 10% of 749 from 749, or more intelligently, find out what 90% of $749 is, you'll get $674.10. Okay, so what did we do here? We applied the sales to the price. Okay, so if we did this first and this second, and we've always solved things by working our way inside out, then first we applied the coupon to the price, and then we applied the sale to that. So mathematically, using these defined functions that we have up here, we would say that S of C of P is 0.9 times C of P, which is P minus 50. Using the distributive property, 0.9 times P is 0.9P, and 0.9 times 45 is 45. So if we were to go through and always apply the coupon first and then the sale, we would be paying 90% of the price minus $45. Okay, so let's go ahead and see how that compares with the sale then the coupon. So again, I have the same starting point of $799, but this time I'm going to take 10% away first. Well, if I take 10% away, I should already know that I get $719.10. Okay, so again, that was the sale price being applied to that amount. Then, second, I go and take this amount, and I take $50 away from it, because that was the coupon. That's the effect the coupon has. So $715.10 minus $50 is $669.10. Okay, so what did we do over here? Well, first, we did the sale price, and we applied that sale price with the coupon. Okay, so what does this mean mathematically? Well, it means that we have the sales price, which is 0.9p, and that becomes the input to our coupon price. So this was going to be P minus 50, or input minus 50, and our input now is 0.9p, because that's what S of P is. So there's no actual simplification for me to do here, so this is just 0.9p minus 50. Okay? So we should be able to notice that there is a $5 difference in between those two prices. And we can see here from their composition that there is a difference of 5 within each one of those. So if you are a consumer, which order do you hope that these discounts are applied in? Well, you should hope that they're going to do the 10% off sale, then apply the coupon. Okay? But if you're the manager and you want it to seem like it's still the same deal, but maybe the store gets $5 more than it otherwise would, Maybe you want to say that as a company policy or store policy, we take coupons off first before we apply any sales to it. Okay, so you can see here how it's very easy for retail stores to go and manipulate sales. Because if you think about it, if you were to go to a store and they said, oh, take an extra 50% off, and you bought something in the store that was 50% off, it doesn't mean that you get to walk away with it for free. It means it's just a 75% discount. But to the mathematically uneducated, they think they're getting a whole lot better deal than they actually are. Okay? So, we're going to go through and take a look at one more problem real quick. So, this one involves volume and time. So this one says a spherical balloon is being filled up at a helium tank. The radius of the sphere increases at a rate of 2 inches per second. What is the volume of the sphere after 2 seconds, 4 seconds, and 6 seconds? Write a composite function that determines the volume of the sphere as a function of seconds. So this one is kind of going to look similar to the pebble in the pond problem, but obviously we're going to be dealing with volume this time. Right? So anytime that I can draw an illustration, I'm going to choose to. So let's just say that we've got a sphere. And if you don't know how to draw a three-dimensional sphere, just draw a circle and then kind of draw an oval that's kind of in it. Yeah, looks like a sphere, three-dimensional. Okay, that's the center. And I know that my radius, okay, is going to be the distance from the center of that sphere to any outside edge of that sphere. All right? So, looking at this, it tells me that the radius of the sphere increases at a rate of 2 inches per second. So the radius of the sphere is dependent on time. So depending on how many seconds have passed, that will tell you what the radius is. So the radius is 2 inches per second. So for every second, it's 2 inches longer. Okay? So we would say that r of t equals 2t. If I go and take a look over here, and I try and figure out that we're also looking at the volume, okay, hopefully you remember volume is a function of the radius. Okay, in order to find the volume of a sphere, you have to know what the radius is. And hopefully we all remember that the volume of a sphere is 4/3 pi r cubed. Okay? So if we go ahead and write the composite function for this, I know that the volume depends on the radius and the radius depends on time. So with your forces combined, we have V of r of t. Because again, if I think about my steps, I have to know the time to figure out the radius, and I have to know the radius to figure out the volume. It's just what piece do you need before you can move on to the next one. Okay? So, if I go and do this composition right here, V is 4/3 pi times an input value that is cubed. Okay? R is our input, that's our input. What is our input? Our input is the function r of t. What is r of t? Well, it's 2t. So V of r of t is going to be equivalent to 4/3 pi times 2 cubed is 8, t cubed is t cubed. Okay, so this could then be expressed as, not sure what's going on with my camera here, so I'm gonna stop it. And now that we've come through the other side of the mathematical vortex, let's get back to it. So we've gotten to the point where we said that our composition function is going to be 4/3 pi times 8t cubed. Well, guess what? I can actually further simplify that. So I can multiply the 4/3 by the 8. 8 times 4 is 32. So I have a 32/3. And then I have pi t cubed. So this right here is going to represent our composite function that we can use to evaluate the volume of this particular spherical balloon after any number of seconds have passed since we went and hooked it up to the helium tank. So let's go through and figure out what it's going to be after 2 seconds, after 4 seconds, and after 6 seconds. But we'll use the composite function, okay? So first, if I want to go through and find it at 2 seconds, that means that I'm finding the volume, which is dependent on the radius after just 2 seconds. So using my composite function here of 32 over 3 pi times our input value cubed. My input value here is 2. 2 cubed is 8. So if I go through and multiply all of this together, okay, I can have 32 times 8 in my numerator, so that's 256. Okay, still going to have a divisor of 3, and that's going to be pi. So 256 over pi cubic inches is what that's going to be. Okay, now if you needed a decimal approximation for that, you can of course do 256 divided by 3. It would get you 85 and a third, and multiply that by pi, which you can either do as pi or 3.14, and you would get approximately 268 we'll call it 0.8 cubic inches. Okay, what about finding the volume at 4? Well, we're finding the volume, which is dependent on the radius after 4 seconds has passed. So that'll be 32 over 3 pi now times 4 cubed. Because again, this is our input value. That's determining our radius. Radius determines the volume. So again, we could go through and say 32, and we can multiply that by 4 cubed, and that's going to give us 2,048. So that's 2,048 in the numerator, just a 3 still here in the denominator, pi inches cubed. And if we wanted a decimal approximation, we could go back to the calculator for that. Do 2,048 divided by 3, multiply that by pi, and we would get 2,144.66 cubic inches. So as you can see, the volume of this is going up tremendously from 2 seconds to 4 seconds, okay? That's a lot of helium to go through and put in at one time, okay? So now we'll take a look at the third one where we have to find the volume after 6 seconds. So we're finding the volume, which is dependent on the radius, which is dependent on the amount of time, which in this case is 6 seconds. So that's going to be 32 thirds pi times t cubed. T is 6, so 6 cubed. So to figure out the numerator here, we can do 32 times 6 cubed, and that'll give us 6,912. Still over 3, because I have a denominator of 3, okay, and that's going to be pi inches cubed, which, if I needed a decimal approximation, again, going back to the calculator, so 6,912 times pi, and then go through and divide all of that by 3, and we get 7,238.23 cubic inches. All right, so by doing the function composition and creating a single function that allows us to answer a multiple part question, it actually makes the number of calculations that we're doing less, and like they say, less is more.